Good evening, ladies and gentlemen. This is
Okay,
Kristine
great.
Guevarra, an instructor at the School of Arts and Sciences of the National University Philippines. I'm here to present to you our research paper entitled Exploring the Impact of Multiple Representations on Algebra Learning. Life is surrounded by mathematics. It helps people to think critically, to infer, and to reason out on certain situations. Mathematics is one of the basic subjects that is necessary to be taught in all levels of education. Learning mathematics in school is not as simple as other subjects. There must be an active participation and involvement of the students in the learning process. In mathematics learning, students are never or seldom given the opportunity to present their own representation because the students tend to imitate the teacher in solving the problem. Perhaps this is due to the limited knowledge about mathematical representation of teachers and their role in the learning of mathematics. As a result, the ability of students does not develop a mathematical representation. Algebra has various representation systems to express ideas and processes, making it one of the cornerstones of mathematics. This elicits the need for multiple representation-based instruction. Algebraic reasoning involves representing, generalizing, and formulating patterns and regularity in all aspects of mathematics. According to National Council of Teachers of Mathematics Standards, to think algebraically, one must be able to understand patterns, relations, and functions, represent and analyze mathematical situations and structures using algebraic symbols, use mathematical models to represent and understand quantitative relationships, and analyze change in various contexts. Since algebra is one of the subjects that seem to be least concrete for pupils, they find algebra challenging. Due to its difficulty, it puts forward serious obstacles in the process of effective, meaningful learning in mathematics. Multiple representation-based instructions using the concept of multiple representations in connection with the teaching and learning of mathematics. The concept of multiple representations includes identifying a mathematical idea in a set of different representations, manipulating the idea within a variety of representations, translating the idea from one representation to another. Constructing connections between internal representations is one's network of representations, being able to decide the appropriate representation to use in a given problem and identifying the strengths and weaknesses, differences and similarities of various representations of a concept. Representation was generally defined as providing the same information in more than one form. Representations can be categorized in two classes, namely internal and external. Internal representations are defined as individual cognitive configurations inferred from human behavior, describing some aspects of the process of mathematical thinking and problem solving. On the other hand, external representations are defined as structured physical situations that can be seen as embodying mathematical ideas. External representations are the main focus of these current studies. Instructional approach is an important factor in the learning performance of students. Filipino students perform weak in mathematics as reflected in Science and Education Institute study on trends in mathematics and science study in 2003 because students view mathematics as a body of unrelated facts and procedures rather than as a unified system of concepts and operations that state certain patterns and relationships that exist in the real world. Persistent lower performance of Filipino students in mathematics. As evidenced by the 2014 National Achievement Test, scores and international assessments underscores a need for innovative instructional approaches. For the theoretical framework of this study, it is anchored under the theory of multiple representations by Jerome S. Bruner. According to him, the power of a representation can be described as its capacity in the hands of a learner to connect matters that on the surface seem quite separate. This is especially crucial in mathematics. Bruner suggested that development of concepts involves successive restructurings of facts and relations, which came from children's interactions with and active manipulation of their environment. With that, he recognized the three modes of representation, namely enactive, iconic, and symbolic, that must be present at all stages of development. In an inactive representation, it can only demonstrate the past through appropriate motor experiences. However, in iconic representation, it employs the use of organizational structures, spatial signifiers, or images to represent past experiences. In symbolic representation, design features that can include remoteness or arbitrariness represent the past. For the statement of the problem, three questions has been identified. First, what is the level of performance in algebra of the control and experimental groups? What is the significant difference in the algebra performance of grade 9 students exposed to multiple representation-based instruction, or MRBI, and those exposed to the conventional teaching method? Lastly, is there a significant relationship between students' perception of MRBI and their algebra performance as measured by their post-test scores? For the conceptual framework, the conceptual framework illustrates the relationship between MRBI and student algebra performance. At its foundation, the framework shows two instructional approaches being compared, MRBI and the conventional teaching method. MRBI is characterized by its integration of multiple representational forms, verbal descriptions, graphs, equations, and their combinations, which collectively support diverse learning modalities. These components feed into the learning process where students develop conceptual understanding, engage in and active learning, enhance problem-solving skills, and gain multiple perspectives on algebraic concepts. The framework demonstrates how this enriched learning process leads to improved student outcomes, including enhanced algebra performance, stronger problem-solving abilities, deeper conceptual understanding, and overall academic achievement in mathematics. Two moderating variables, namely student perception of MRBI and implementation duration, are shown to potentially influence the effectiveness of the instructional approach. This reflects the study's finding that while MRBA proved more effective than conventional teaching, student perceptions of the method did not significantly correlate with performance, and a longer implementation period might maximize benefits. The directional arrows indicate the hypothesized relationships between these components, illustrating how teaching methodology influences learning processes and ultimately impacts measurable student outcomes in algebra. The research methodology chart shows the step-by-step process used to study whether MRBI helps students learn algebra better than traditional teaching methods. The study began by identifying the research problem. Many students struggle with algebra when taught through conventional methods. Researchers then selected 62 ninth grade students from Kapayapaan National High School based on their first-term grades. All students took an algebra pretest to measure their starting knowledge. After testing, they were divided into two equal groups of 31 students each, a control group taught with conventional methods and an experimental group taught using MRBI. After the teaching period, all students completed both an algebra post-test to measure their learning and a survey about their perception of the teaching methods. Researchers then analyzed the data using statistical tests, namely t-tests and correlational analyses, to determine if there were significant differences in performance between the groups. The analysis revealed that students taught with MRBI performed significantly better than those taught conventionally though interestingly, there's no strong relationship between how students felt about MRBI and how well they performed. This straightforward experimental design allowed researchers to directly compare the effectiveness of the two teaching approaches under similar conditions. To discuss the findings, Table 1 shows the pretest level of performance of the control group and the experimental group in algebra. It presents the data used in the comparison of the pretest results of the two groups. The mean and standard deviation of the control group and experimental group are 11.06 and 2.33 and 10.83 and 1.98 respectively. According to the result, the level of performance of the control group and the treatment group in the pretest did not differ from each other. The level of performance of the participants before the implementation of both MRBI and conventional teaching approach is equal, which the result approximates good estimate of a more capable result. Table 2 shows the data used in the comparison of the posttest results of the two groups. The mean and standard deviation of the control and experimental group are 10.06, 16.06, and 2.45, and 20.63 and 3.32 respectively. Table 3 shows the test of significance through comparison of the control group strategy. The t-test independent sample was used in the scores of participants in comparing their pretest and posttest. Based on the result, in the conventional teaching method, t-test generated the absolute value of t computed negative 12.078 that is greater than the absolute value of the t tabulated positive negative 2.030. In this case, the decision failed to accept the null hypothesis, which means that there is a significant difference between the performance of the controlled group in their pretest and posttest. The result shows that the controlled group exposed to conventional teaching improved from their pretest to their posttest. This shows that conventional teaching method is still effective since in the first place the implementation of K-12 approach gave birth to the learner-centered environment. Table 4 shows the test of significance through comparison of the experimental group strategy. The same test was used to determine the difference between the pretest and posttest results of the participants exposed in MRBI. It resulted to the absolute value of t computed negative 13.959 that is greater than the absolute value of t tabulated positive negative 2.045. In this case, the decision failed to accept the null hypothesis, which means that there is a significant difference with their pretest and posttest. Lastly, Table 5 shows the relationship between the perception of the treatment about MRBI and posttest score in algebra. Based on the given table, the means of the posttest scores and perception of the experimental were 20.63 and 3.44 respectively. The correlational analysis resulted to a computed R value of 0.1088, interpreted as very low correlation, which is less than the R tabulated of 2.048. In this case, the decision accepted the null hypothesis, which means their perception has significantly no relationship with their posttest scores. The result shows that the posttest score and the perception of the participants in the MRBI were not related to each other. Conclusions are derived from the result. First, multiple representation-based instruction significantly improves algebra performance among grade 9 students compared to conventional teaching methods, as evidenced by higher post scores in the experimental group. Second, students exposed to MRBI demonstrated stronger problem-solving abilities in algebra, suggesting that multiple representational approaches foster deeper conceptual understanding. Lastly, there is no significant relationship between students' perception of MRBI and their actual performance, indicating that effectiveness is not dependent on students' subjective experience of the teaching method. For the recommendations, the researchers recommended school administrators to consider implementing programs or comprehensive training in MRBI methodology, focusing on effective integration of multiple representations in their algebra lessons. Teachers may incorporate combining MRBI with educational software and digital tools to further enhance the student engagement and provide interactive representation. And lastly, future researchers may conduct further studies focusing on the effectiveness of MRBI across different grade levels, mathematics topics, and student demographics to establish its broader applicability. That's all. Thank you for your listening. I am now open for questions.